Academy, and we are looking at Jordan canonical forms. This is a topic in linear algebra, which is very important in pure mathematics and also in application of computer applications. So if you have not subscribed to this channel, kindly subscribe, and if you have not shared with your friends, also remember to share with them. Let alpha be a eigenvalue for this matrix, square matrix of a multiplicity which is greater or equal to 1. Then I want to introduce something which is very important while we are discussing about Jordan canonical forms, which we call them Jordan blocks. So if you have J1 lambda, we mean that is a Jordan block of size 1. A Jordan block of size 1. With alpha, with the lambda being one of the eigenvector. So for the first one, it will be just equal to the lambda or the eigenvector given. Then second one is J2 lambda, which is the Jordan block of size 2, which is basically this upper triangular matrix with the lambda or the eigenvectors across the main diagonal and the one taking the next position upwards. Then J3, which is Jordan block size 3 of the eigenvector lambda, or which the eigenvalues will take the main diagonal and the other positions are filled with 1, just a position after algebra 1, but the third position takes zeros. So you have to note that. So that if, for example, we want to write Jordan block of size 4, we'll have J lambda will be equal to algebra 1 0 0, then 0 alpha 1 0, then 0 0 alpha 1. Are we there? 1. Then we'll have now the 0 0. Okay, sorry, you'll have 0 0 0. So it will be because I can't, it's not working there. The last level is 0 0 0 algebra. So something like that. So it's alpha, then the next. So that is the size 4, the Jordan block size 4, and so on and so on, and so on and so on. So this is very key to note. That's how we write Jordan blocks. So let's pose this kind of a question here. What is the minimal polynomial for the Jordan block of size k? Jordan block of size k. Let's look at this. If we let A be the first Jordan block size 1, then its minimal polynomial will be basically being given by x, and mark is that x minus alpha, lambda, which is the eigenvector. So if you reduce this x, you substitute with the first block, then it will be like saying this, which is automatically being 0, because you know the first size block, Jordan block size 1 is alpha. So it's like you're having alpha minus alpha, which is equal to 0. Same way you do for Jordan block 2 size 2, this will be the correct minimal polynomial. So this subscript here will mean the power. So this, if you look at this gives us 0. It gives us 0. So if you do also for J2, as we have just said, you'll find that the 2 is like the EDC, or the power of the polynomial, of the minimal polynomial. So if it's 2 here, then its minimal polynomial will be 2 power x minus lambda power 2. And if you substitute clear here, you'll find it also giving you a 0. So and so on and so on. So in general, the minimal polynomial for the Jordan block size k is actually given by the x minus lambda power k. Remember, k in this case is the multiplicity or the power. So this k here is basically this one here. So it just follows like that. Okay. So let's look at this claim. If you have A, which is a square matrix with eigenvalues lambda 1, lambda 2, all that to lambda k, or multiplicities m1, m2, all that to mk, then if you sum the multiplicities, you'll find that the multiplicities will give you the size of the square matrix n. Since there are n eigenvalues, counting multiplicities. Okay, so the Jordan block for x lambda high, or multiplicity mi, is actually j lambda high. So that's true. It's true. It's a claim from what we have just looked at. It's actually, it follows. Then the upper triangular matrix similar to A can be decomposed in terms of Jordan blocks. That's noted. If x minus lambda high has multiplicity which lies between 1 and mi in the minimal polynomial, then the largest Jordan block associated to xi will be of size ri. That will be the minimum, because the minimum will have to follow that. So having noted that, again, if there are no repeated factors in the minimal polynomial, then the largest Jordan block are of size 1. And so you'll say that A will be diagonalizable matrix. And if it happens that there is a factor x minus alpha power ri for r greater than 1 in the minimal polynomial, there is a Jordan block. There's a Jordan block of the same size ri, and that will mean that A is not diagonalizable matrix. It will mean that A is not a diagonalizable matrix. So if you have any question of any bit of what we are discussing here, kindly just leave a comment. If you have a question that you need us to tackle, you can also leave it like a comment. And remember to subscribe if you have not yet subscribed to this channel. Let's look at an example. So if you have this A given of that, which is a 3 by 3 matrix, and you find that its characteristic polynomial is given like this, you know how to find polynomial, characteristic polynomial from our previous tutorial. So if you have not checked on that, you can go back and check it. It will give you a very good guidelines on how we come up with the characteristic polynomial. So as we are saying, you'll find that the order, the order of A, this A, which we know is 3, can be just be reduced from the powers of the characteristic polynomial, because this part here is power 2 and this is power 1. So the order of this matrix is actually 2 plus 1 equal to 3. What we are saying, m1 plus m2 equal to the order. So it follows like that. Now we have a minimal polynomial, which is actually same as the polynomial, characteristic polynomial px. And if you can break this, then a will be approximately that the combination of Jordan block size 1 and 2, because remember these two gives us the size of the blocks, which is actually this, that's block 2, and block 1 is that, which is actually a transposing composition, Jordan composition. You'll find that is true. You'll find that one is true. So if you have any question of either of these, you can just leave a comment, subscribe, leave a comment, and also write anything on the comment for any question that or any elaboration that you may need. This is the Vika Academy. We are here for all those questions. Now subscribe if you have not yet subscribed, and remember to share with your friends. Until next time.